In this example, suppose that cell phone bills for residents of a city have a mean of $70 and a standard deviation of $9. Random samples of 50 cell phone bills are drawn from this population, and the mean of each sample is determined. Part A. Find the mean and standard error of the mean of the sampling distribution. Part B. What is the probability that a sample of 50 cell phone bills selected at random has a mean greater than $69? So, assuming that X represents the values of the cell phone bills of the residents of this hypothetical city. So, X has a distribution that has a mean of $70 with standard deviation of $9. Since we are assuming that we are taking samples of size 50, so n is 50, and this is considered a large sample, we have that by the central limit theorem, the x-bar distribution, the sampling distribution yielded by this underlying population distribution is normal because we have a large sample. And now we're going to determine part A, which is the mean of the sampling distribution and the standard deviation of the sampling distribution. So the mean of the sampling distribution is the same as the mean of the population, and the mean of the population is 70. So the mean of the sampling distribution is equals to 70. Now, the standard deviation of the sampling distribution is given by the standard deviation of the population divided by the square root of the sample size. Therefore, we have that the standard deviation of the sampling distribution is equals to 9 divided by the square root of 50. So the result is approximately 1.27. So if we use one decimal place, is 1.3. To find what's the probability that a sample of 50 cell phone bills selected at random has a mean greater than 69, it means we're trying to find the probability that the x-bar value of the sample, meaning the mean of the sample, is greater than 69. Since the sampling distribution is normal with mean of 70 and a standard deviation of 1.3, we can convert the x-bar distribution to z-scores, meaning we're going to work with the standard normal distribution instead. So the probability that x-bar is greater than 69 is the same as the probability that the z-score is greater than 69 minus 70, which is the mean of this x-bar distribution, divided by the standard deviation of the x-bar distribution. So this is the same as the probability that the z-score is greater than negative 0.769. Let's round this number to 2 decimal places. So negative 0.77. The probability that z is greater than negative 0.77 is corresponding to the right-hand side area of the score negative 0.77. To compute the area to the right of negative 0.77, we're going to rewrite this area in terms of left area. So the right-hand side area is equals to the total area under the standard normal curve, is the total area under the standard normal curve, minus the left area of negative 0.77. So this is equals to 1, the area under the standard normal curve, minus the area to the left of negative 0.77 under the standard normal curve. Looking up this value at the normal distribution table, we have that this is equals to 0.22 0.06. So the result is 0.7794.